Okay, so just continuing now our work here on the generalized or the extended binomial theorem. And just to recap, what we discovered, what we looked at, was an expansion of 1 plus x to this power of n here, where n, well, we just spread our wings a little bit, didn't we? We said that n could be a member of the set of rational numbers, and no commitment on the irrationals, but certainly on the rational numbers, so fractions, negative integers. And we looked at an expansion of a binomial with these sorts of powers, and we looked at we looked at our coefficients, and we decided that we can simplify these guys, right? We can simplify these guys in this way, that when we, by definition of what these NCR notation means, we can simplify using our understanding of factorials to, and I'm just replaying the first few out just to recap this. So it's worth doing, isn't it? Just to remember what the factorials mean. We need to keep that at the forefront for the rest of this course, really. So I'm just writing it out now, because what this is just how we got to the position we got to the other day, and that is, we were able to simplify everything down. So all our coefficients, and we did concede that this was only relevant for values of x between -1 and 1. Okay, so as the terms get larger in ascending powers of x, then the value of those terms diminishes. So in summary, 1 plus nx, and you can see what's happening here. nc1 has become n. nc2, which is n over, n minus 1, n minus 1 over 2 factorial squared, n minus 1, n minus 2 over 3 factorial x cubed. Then we brought in our general term. So it's somewhere along here. There's an r term, which is n minus r plus 1 over r factorial. That's x to the r. And it goes on. So, and this is an infinite sum. This goes on forever. Okay, so this is what we determined, and this is correct for values of x between 0 and 1. For values of x outside that, all bets are off, because you can see what happens to these terms as x gets larger. It's not converging on anything. And what this says more than anything is that we've got this endless, infinite sum that just seems to arrive magically at this value here. Well, we've seen something like this before. We've seen something like this before in a part of the course. Well, just earlier on in this unit of work, in fact. We've seen this sort of thing, 1 plus x squared. What do you know what the next term's going to be, and you know that because I'm following a pattern, and that pattern it's a recursive pattern. I'm multiplying by x each time, and that gives me a common ratio of r. And okay, we also know that this is an infinite sum, and infinite sums do exist for common ratios between -1 and 1. So if I could say that this is equal to, if x is between -1 and 1, I can say it's equal to u1 over 1 minus r being x, if x were to lie between -1 and 1. Okay, so that came up in geometric series, and it's this idea that if we've got diminishing if we've got diminishing terms in a series, then it's the value of those terms becomes smaller and smaller because you're multiplying by less than 1. And so by the time you get to the thousandth, millionth, 10 millionth term, they are so infinitesimally small that they're having a very minor effect on the sum of this expression now. So whilst this sum is never going to reach a certain amount, it's going to get closer to it. It's this idea of a limit, very important in mathematics. So we call that a convergent sum or a limiting sum, and this is what we've arrived at, 1 over 1 minus x. Now let's see if we can marry these two ideas, because what I've got in the light blue up here is, well, this was our extended binomial theorem result from the other day, where we thought, well, okay, I can rewrite this. I can rewrite my factorial notation, and so now I'm not relying on this n going down to 3, 2, 1, because I'm able to do a simplification. And as x increases in power, then if x is between -1 and 1, then they're going to fade out of the reckoning, and we are going to converge on a sum. And so that sum is there, 1 plus x to the power of n. So let's see if now our two ideas here can merge, and that would be a nice thing to round this whole topic out that we've been doing. So let's just check it, shall we? So let's make so what we're saying here, if I just reverse this around, this is saying that 1 minus x here to the -1. What this is suggesting is that it was 1 plus x squared, and we know that to be the case. So let's just check our binomial theorem to see if it works for this example. So we're going to let x equal -x, n equal -1. So we're just going to do this here. We're going to replace x with -x, and we're going to let n equal -1. And we're going to run it through. So it'll be 1, then it'll be n, which will be -1 by x, which becomes -x. N becomes -1, n minus 1 becomes -2. That's over 2 factorial, which is 2. X becomes -x. And we square that. Let's get it through the next term. It'll be -1, -2, -3 over 3 factorial by x cubed, or not x cubed, but -x cubed, and this goes on. Okay, so let's see how this looks when we simplify it. So 1, we've got plus x here. This looks like it's positive 2 over 2, so that's just 1. -x squared is x squared, so that's just plus x squared. This looks promising. -1 times -2 times -3, well, that gives -6 over 6, so I'm on -1, but this is -x cubed. Negative times negative brings me back to positive. I've got x cubed. This looks very promising. So it seems to work. Our extended binomial theorem works in something that we know. So it's a nice little reassuring cross-check against another area of the course that we've looked at. So in blue, that's our extended binomial theorem, and we can use that for not just positive powers of positive integers, but we can use it for all rationals. And I'd just like to do another example, just maybe a tougher one, that just as a bit more practice, and then we'll finish off the last exercise in this chapter. Okay, so it might be a good idea now to hit pause and see if you can do this. This is similar to, so I think question 3 in the textbook, the one that I gave as a challenge question the other day. You might have already done it, but this is a good one to do. Don't have a peek in the textbook. Just press play. Just pause it. Have a go at it. If you get stuck or you get through it and you want to check your answer, then hit play again. And let's see if we can agree on how this one works. Okay, so square root of 1 plus x over 1 minus x. So this would need to be rewritten using index notation. So we'll write it as 1 plus x. We'll split our thirds up like so, which we'll then be able to write as in one line as the square root of 1 plus x. In fact, let's get our fractional indices in place now. 1 plus x to the half times 1 minus x to the negative a half. Okay, so we're looking at a a product of two expansions here. So we might do them one by one. So we'll get on to 1 plus x to the half. We'll do that guy first. So 1 plus x to the half equals. Okay, this is in reasonable format for us. So we'll be able to write it as, so really n is just becoming a half for us here. So we've just got 1 plus 1 half. I don't need to do anything with my x. Now I've got n by n minus 1, so that's just a half by negative a half. That's going over 2x squared, and a half, subtract 1, subtract another 1, and that's all going over 6, or 3 factorial, that's x cubed. So that's going to continue. Let's simplify what we've got so far. So 1 plus a half x. This is negative a quarter, so it's negative 1/8 x squared. This is 3 over 8, 3 over 48. 3 over 8 divided by 6, 3 over 48, or 1/16. And it looks like it's positive 1/16. 1/16 x cubed. And that is going to continue. Let's have a look at what at 1 minus x to the negative a half. There's a few more things going on with this one, but n is now equal to negative a half, and our x has become negative x. So it's doing something like this. We're starting at negative a half, and we're still subtracting 1 each time, dividing by 2. This has now become negative x squared. And if we just bring into the equation the power of 3 as well, and we'll see if we can spot anything going on. Just subtracting 1, that'll become a 6 there, and it's negative x to the power of 3 there. So we can see that we get still got plus a half x here, but I sense that's going to be a plus as well. This all works out to be 3 over 8 x squared. Now I think I'm going to get negative x cubed here, but I'm going to get a negative here. So I think everything's going to positive out with this expansion. So it'll be 135 over 248. Sorry, 1315 over 248. 15 over 8, divide that by 16, 6, that's 15 over 48, or 5 over 16. So it looks like plus 5 over 16 x to the power of 3, and that goes on. Now, if we start to have a look at this expansion, and the reason we don't need to get into too deeply into this is because we do know that x, my value of x, the absolute value of x is between, the absolute value of x is less than 1. That's shorthand for x is between negative 1 and 1. It means the same thing, just a shorter way of writing it. Now, that means that once we get into those powers of x, 4, 5, 6, then we are looking at very, very small values, so they become less apparent. And so what we've got here, and this is an important bit of notation, it's approximately equals to. So we're just looking to see where this thing heads. So if we look at the product of now our 2, so therefore we could write that 1 plus x to the half multiplied by 1 minus x to the negative a half. Well, you know, this is 1 plus, it's a half x, it's minus an 8th x squared, it's plus 16th x cubed. All right, let's just have a little look at that roll out, and let's compare it to this. Plus a half x, plus 3/8 x squared, plus 5/16 x cubed, and on we go. So let's, what do we get? So our first set early of multiplications, or our pairs, 1 times 1, that looks solid. 1 times a half x, so we get a half x in there. 1 times 3/8 x squared, so we better bring that in. Now, how far do they want us to go? They take us up to x squared, okay? Because once we get to x cubed, we could get 5/16 x cubed in there, but that is now starting to take on a very small value. So we'll leave it at that. Really, there's a bit more to do, But once we get into minus a half x, so we'll just bring that into play. 1 times, so I'm now bringing in this term here and running it through each of the terms in the second bracket. So I'm just to explain what order I'm doing things in. So that'll be now a half x, so I'll add a half x in there. Then it's a half x by a half x, that's a quarter x squared. Then it's a half x by 3/8 x squared, so that's, what's that, 3/16 x cubed. 3/16 x cubed, and that'll go on. But we're really only taking it to x cubed, so I'll take it to the next term, minus an eighth. I'm looking now at negative 1/8 x squared and running it through there, so that'll be minus 1/8 x squared. I'll go to the next term, that's minus 3/64, but then that's x, minus an eighth x squared times minus a half x. Positive a half x, so that's minus 1/16 x cubed, minus 1/16 x cubed, and that's as far as we go. I could put this one here in place, so that's plus a 16th x cubed, so they seem to have cancelled each other out, those two there, minus a 16th and plus a 16th. So let's see what we've got in terms of recognition that goes on for a bit, but we are just now saying, well, let's say that that's approximately equal to, we've got this 1 here, so that's nice and in place. I've got a half x plus a half x. Does that look promising? Yes, I want x. So let's start to move things on. So a half x plus a half x, there it is there. So that gives me x. Now I've got 3/8 x squared. It doesn't even look like, did I get to, I'm not even getting to powers of 3. So 3/8 x squared plus a quarter x squared. That gives me 3/8 plus 2/8, that's 5/8 x squared. Subtract 1/8 x, 4/8 x squared, so that's, what's that? That's a half x squared. And that's as far as we go. We're not taking the cubics into account, so that's as required. Quite a bit of messing around to be done there. Okay, so I think let's go on now and complete exercise 1. I think it was J, and we can look at questions 3 through to 7.